to the Friday Math Happy Hour. This week, we're going to be talking about logic statements, truth tables, conditional and biconditional statements. And let me just get started. So, interestingly enough, logic is something that is used in many places, such as in law school. Often, students of law take logic so that they can build valid arguments or like convincing arguments when they're creating a case. I would say in general, logic can be used to communicate. Even back in the Greeks, they would study logic so that they would make same thing, convincing arguments. Logic also, it's applying computer science, as you will see. A lot of the logical symbols and operations that we do also appear on computer science and also in electrical circuits. So those are just a few of the applications for logic. Let me move on. So in the first thing in mathematics to start to study logic is understanding what is a logic statement. What is a statement in mathematics? And we have different types of sentences. For example, we have sentences such as, is the test today? Which is a question, of course. We also have another sentence, go get the newspaper. This is what we call a command. Another sentence would be, this is a nice car. We call that one an opinion. And the last one, Denver is the capital of Colorado, which is a statement of fact. In this section, we focus specifically on those statements similar to the last one, where we're stating a fact where we can say whether it's true or false. So for us in mathematics, a statement is going to be a declarative statement that is either true or false, but not both at the same time. So anytime that we talked about a statement, we need to be able to determine this is true or this is false. Maybe in some cases, we're going to see that we allowed it, that it might be uncertain, but it can only be one or the other, not both at the same time. And going back to the examples, the question, is the test today? In mathematics, we don't consider that a statement because we cannot say true or false. That's rather a question, so we cannot give it a truth value. Similarly, commands or opinions are not really statements in mathematics. Let's see examples. Denver is the capital of Colorado. That was my indication that one is something that we can say is true. If I were to say maybe Austin is the capital of Colorado, then we know that that's false. That would also be a statement. So statements are things that we can classify as true or both, but true or false, but not both at the same time. And here's some more examples. Let me increase this a little bit. First statement says, the instructions is to determine whether each sentence is a statement. A reads, Florida is a state in the United States. And this is, of course, a statement because that is true. Florida is a state in the United States. The next one, which is B, the sentence is, how are you? Well, we know this is a question, so this is not a statement. Not in mathematics. Mathematics statements are only those ones that are declarative, where you can give a truth or false value. So all other sentences are not considered statements. The next one, open the door, also is not a statement because that's more of a command. Letter D, example, reads, in the year 2024, the President of the United States will be a woman. Now, given that we are in 2025, we know this was false. So letter D is a statement because it has a value. But even if this year was a future year, for example, if the statement was, in the year 2029, the president of the United States will be a woman, these would still be considered a statement in mathematics, because that statement you can actually say false or true once the time arrives. At this point, we might not be able to classify it, but we know for sure that it has to be one or the other. It cannot be both. So the year in this question is not relevant. And even though, like, at this point, we can say that it is a false statement, even if it's a future year, the fact that that is uncertain, that it hasn't been determined, doesn't matter. All that it matters is that when that time arrives, it will become true or false. So surprisingly, letter D is a statement, even if it's a future year. The next letter, E, says 7,555 is a large number. Well, this one, when you analyze it, this is more of an opinion, kind of like in the previous example, because how do you classify if something is a large number? You know, maybe someone that is dealing with stocks would say, like, no, that's not a lot. A lot would be 100,000 or a million. So that class, whether you classify if it's large or not, that's not something that it's set or fixed for everybody. So this is more of an opinion. Therefore, is not a statement. Letter F. Letter F is also a very interesting example, because if you read it in symbols, and this is something I always remind my students, in mathematics, we could create statements and sentences with symbols. So if you read it, this would say X is greater than 3. And you would be thinking, like, well, how do I know what X is? We need to know what is the number that X represents in order to determine if it's true or false. But it's kind of like letter D. Even if you don't know the specific value, so at this point it's uncertain. We don't know what number X is. The fact is that if you put 5, if X is 5, then you would say 5 is greater than 3. That would be true. If you put maybe 1, then it would be false, because 1 is not greater than 3. So because this sentence it actually becomes true or false once you substitute X with a number, we're gonna call it an open statement. So it is a statement, but it is open because it's missing the actual number for X. So this is another type of a statement. Like I said, you can think about it that it's gonna be true for some values, for some numbers, and it's gonna be false for other numbers, but it's never gonna be both. Therefore, it's considered a statement. Letter G. Now, this is 9 to the power 9 plus 2 is a prime number. Well, 9 to the power 9 plus 2 represents a number. I will need to get on a calculator and raise 9 to the power 9 and then add 2. And that's probably like a large number. I'm not even going to say what number it is. But because it is a number, numbers, you can classify them as prime or not prime. The only thing that I need to be a prime number, it has to be a number that only has 2 factors, that it is only divisible by itself and only divisible by 1. Such as 3. 3 is a prime number because it's divisible by 1 and by 3. So it has exactly 2 divisors. So even though this is going to be a large number, and I don't even want to guess it or get on a calculator, the fact of the matter is that once you put it in a calculator, you'll be able to determine whether it is or it's not. So it has those 2 possibilities. This sentence has the possibility of being truth and also has the possibility of being false, but not both of them, because since it is a number cannot be both. It's either prime or the opposite would be composite. Therefore, G is an example of a statement because this number is either going to be prime or not. It doesn't matter what it is. So this goes back to me, as I was saying before, when you have sentences, it doesn't matter if they're true or false. As long as you can determine whether it's true or false, that's all that really matters. So letter G is an example of a statement. And the last one, which is H, H is pretty similar to F. This is an open statement because since we don't know the value of X yet, we cannot tell if this is true or false. But the point is that once you substitute X with a number, this statement will become true or false. In fact, we know that the only number for which X is true is if X is 4, because 4 plus 1 would be equal to 5. If X is any other number, it's going to be false. And therefore, because it has those two possibilities only and it cannot be both at the same time, it's considered an open statement. So that was my last example. Okay, so the next part is when we have statements, we can have what we call a simple statement, which conveys a single idea. I also say like it's a single sentence. And a compound statement is if you have 2, 3, or more sentences. So the word compound usually means like you have, it's composed from different things. So it's more than one. So simple, it's a single one. Compound is 2 or more. And the way that you would have more is by, for example, you could create compound statements if using connectors such as and, or, if, then, and if and only if. In fact, we're gonna spend a good amount of time studying these connectors. So for example, I have two simple statements. It says, I will attend the meeting, and the other one is, I will go to Friday happy math hour. I could connect them by using the or, which it makes a larger statement. So it says, if I read it all together, the compounding statement would be, I will attend the meeting, or I will go to the Friday happy math hour. Let me move on to the next slide. Now, in mathematics, we all the time we're using symbols to kind of like shorten. It just makes it simpler to represent. So even for sentences, we also have symbols to represent these connectors. And so on the table, you can see that the first connective, we call it the negation. And we represent it by using, I call it the wiggle line, where it says in symbolic form. So statements are going to be represented by lowercase letters such as P, Q, R, S, W. We usually use those type of letters, although it could be any letter. And if I want to say the opposite, the negation of P, the opposite of what P is saying, then I use that wiggle line next to P. If I want to connect two sentences or two statements, P and Q, the symbol that represents that preposition, that connector, and, is going to be kind of like a triangle. And we call it the conjunction. If I want to connect two statements with the or preposition, then I use kind of like a V letter, and it's called the disjunction statement. The fourth one, this is on the fourth row, this is kind of a subtle one. It's called a conditional statement. So in symbols, I would read it as if P, comma, if P, then Q. So the connective is kind of like two prepositions at the same time, if, then, indicating that if something happens, then something else has to occur. And the symbol to represent that conditional statement, it's an arrow pointing to the right, going in the direction. The direction is actually important, and we usually write it to the right. And we have the very last one, the biconditional. If, well, I would start by saying P, if and only if Q. So this connector is represented by an arrow that points in both directions, kind of like a double arrow. And the idea is that if something happens, then the other one has to occur. And it goes in both directions at the same time. Like you can work this from left to right and from right to left. So that's what we call it, if and only if. That for one to occur, the other one must occur. Let's move on to more examples. So the next thing is, before we get to those examples, we're also create truth tables to assign the value of compound statements. So if you have a simple statement, it's easy to determine whether it's true or false. But usually when you have compound statements, you gotta analyze the individual, the simple statements to see what is the value and its connectors, what are the connectors involved in that compound statement to determine the value of the whole sentence. And so we usually use truth tables, and the truth tables show all of the combinations. So it's not just one possibility. The truth tables show all of the variations of truth values and what is the final outcome of the compound statement. So I mentioned the symbol for the negation. So what do I mean by the negation? Well, if I have a statement such as today is Friday, the negation of that statement would be today is not Friday. So kind of like the opposite. If, to give you another example, if I would say I am not tall, then the opposite would be I am tall. So the negation is always the opposite. And it is represented by using what I call the wiggle line. Sometimes I see kind of like just a minus symbol. There's like different symbols to represent the negation. The one that we're gonna use in this book is the wiggle line. Now, observe that understanding the negation is pretty simple. The truth value of the negation is pretty simple. If I say today is Friday, this is something that is true right now because today is Friday. So the negation, if somebody else were to say today is not Friday, then we can say automatically that it is false. So this always occurs. If you have a sentence that is true, its negation must be false. And backwards, if we have a statement that is false, then the negation has to be true. So this always occurs with negations. Let's look at example 2. The indication is write the negation of each statement. So starting with A, Ellie Goulding is an opera singer. Well, the negation of that would be, and I think he changed the name. So let me read it again because he changed the name. Jordan is an opera singer. And then the negation would be Jordan is not an opera singer. At this point, we're only writing the negation. The instruction of this is just to write how the negation would sound, how the negation would be. Do not worry whether it's true or false. Just worry about creating the negation. So if I start with Jordan is an opera singer, then the negation is Jordan is not an opera singer. So negations are most of the time, all you need to do is include the not preposition. You just add, if something is, then the negation would be something is not. Example B says the dog does not need to be fed. So this already says that it does not need to be fed. So the negation of this would be that it needs to be fed, right? The dog needs to be fed. So you see, the negation is not always adding the preposition not. If it already has it, then the negation eliminates. So it's the opposite. Let's look at example C. It says the fire engine is not red. Well, the negation of this is the fire engine is red. And last, example D, the Queen Mary II is the world's largest cruise. Well, this is this is what I would say, like, this is in positive form. The negation would be the opposite, that it's not the world's largest cruise ship. Huh? So the Queen Mary II is not the largest, it's not the world's largest cruise ship. So this is examples of how to write the negation given when a sentence has already been given. So you just write the opposite. You create the opposite of what the statement is saying. Now, another type of exercises that we do in logic is representing sentences and statements with symbols. This makes it a little bit simpler when we do the truth tables. So when we do operations and we are trying to make a logical analysis of a sentence, it's a good idea to have like a short writing for these sentences. So notice we have kind of like the labeling. P represents today is Friday. Q represents it is raining. R represents I am going to a movie. And S represents I am not going to the basketball game. The instruction will be write the following compound statements in symbolic form. So A, today is Friday and it is raining. Well, notice this is a compound statement that is using P because P is today's Friday. And it is raining is Q, so it compounds P and Q with the connector and. So in symbols, this would be P, and then that, let's call it the triangle, although it's not a complete triangle. Notice that it's missing the bottom line. So literally, when you're representing a sentence, try to split it into different parts. Oh, notice that here I color coded this. So everything that is in yellow represents P, everything that is in pink represents Q, and then in the middle, the green, the word and is represented by using the symbol that connector had. I'm gonna call it just the triangle by using the triangle symbol. And so the whole statement can be represented in symbols as you see on the right, which is P and Q. Okay, let's do the same thing for B. It is not raining and I'm going to a movie. Well, remember that raining is Q. Since it is not raining, that's the negation of Q. So we represent the negation by using the wiggle symbol. Then we have the and connector, and then to the right, we have I'm going to a movie. That's exactly R. So in symbols, this statement is negation Q or not Q and R. The next example, letter C, it reads, I am going to the basketball game or I am going to a movie. Well, the first statement, I am going to the basketball game, that is actually the negation of S because S says I am not going to the basketball game. So since in C I'm saying I am, that's the negation of S. But now the connector is or, so that's the V letter. You could see it on the table on the right. I have that or connector. And the last, I'm going to a movie, this is R. So the whole statement in symbols is not S or negation S or R. And the last example, it is if it is raining, comma, then I am not going to the basketball game. Well, you might, here you want to emphasize on the prepositions. Usually when I start breaking down the statement into simple statements, then I look for those prepositions, and these ones should stand out, having the if and then combination. So if and then, if we look at the table, we call that the conditional, so there's an arrow to represent them. And the starting sentence, that's the P sentence. Well, in this example, on my table, I use P and Q, but then if I look at the labeling, it says it is raining, so that actually it's Q, that's the letter Q. So I'm gonna start with the Q and then arrow. I am not going to the basketball game. That is S. So in symbols, it will be represented as Q arrow S. And it represents exactly that. So those symbols represent that entire compound statement. So even I usually there's you can do it backwards as well. If you see those symbols, you should be able to write down the whole sentence. If I look at those symbols, I would start by saying if, and then whatever Q is, if it is raining, then I am not going to the basketball game. This is actually the opposite, the way working it backwards. So now we have in this example same letters, but the meaning has changed. So that's totally fine. Just like variables x, y, in different problems, they represent different things. So whenever you're working on a question, make sure that you identify which one is P, which one is Q. So for this example, um, P represents the game will be played in Atlanta. Q, the game will be shown on CBS. R, the game will not be shown on ESPN. And S, the Mets are favored to win. And what we're going to do is we're going to write down, it says, write each of the following symbolic statements in words. Often when you read the book, it would say like, write the statements in English, like write them in words. Use English, not mathematical notation. So A has Q, and that symbol, the triangle, is the and. So the way that I will read it is I would start by, or the way that I will write it down, I will look what the meaning of Q is, which is the game will be shown on CBS, and next, whatever P is, the game will be played in Atlanta. So that's exactly the answer that we have. Now, you might want to have this little table. I'm pretty sure you should have been provided on your course, but if you don't have the PowerPoints, or if the table itself was not put together, like maybe it was breaking down, you could probably go to the book and create your own table. So all of this is on the book. It would be a really good idea to create your own table so that you can quickly reference to the table and know what each symbol represents. So for letter B, again, I'm looking at the and preposition, looks like a triangle, and then the negation of R. So when I write this sentence, I start by writing the opposite of R, which is if R says the game will not be shown on ESPN, then the negation is that the game will be shown on ESPN. And then I use S, which is the Mets are favored to win. So I connect those two by using the and preposition. And last, letter C has S and then the arrow going on both directions. When I start this, notice that I gotta use those symbols, the if and only if. Well, not those symbols, but that writing. So that double arrow means if and only if in the middle of S and negation P. So in words, this would be the Mets are favored to win if and only if. That's like it's kind of like you substitute the arrow by using, or you translate the arrow by using the word if and only if, and then the negation P, which is the game will not be played in Atlanta. Okay. So next, when we have a multiple compound, well, 3 or more, usually you will see parentheses around the symbols. So if you look at my table, on the first arrow, you see parentheses, Q, or not R. So those parentheses indicate that these sentences are grouped together, Q and negation R. When you write this in English, usually we use sentences to separate those groups. So there's like there's a connection, you know, on English in words you would use sentences to make those groups. In symbols we use parentheses because that's the purpose of parentheses, grouping. And so it's kind of like when you do operations with numbers, if you're doing PEMDAS, you start by simplifying what's inside the parentheses because the parentheses indicate that there's a group that has to be simplified first. So in the second row, you see that there's a group created between P and Q. And in the last example, we have two groups. It's P and not Q. Those ones are grouped together. And on the other side of the arrow, you see that R or S are also grouped together. Okay. So as mentioned before, in English, we use comma. So statements on the same side of a comma are grouped together. So for example, in an English sentence, if you have P, comma, and then and Q or not R, then since this to the right of the comma, you have the Q and the R, those ones are grouped together. Notice kind of like the P is by itself. So the ones that are grouped together are Q and R. In the second line, the second row, it says P and Q, comma, or R. Well, the ones that are grouped together are P and Q because those ones are on the same side of the comma, which is to the left of the comma. And last, in the third row, you have if P and not Q, comma, then R or S. This could be one of those where you can have like two groupings. So to the left, P and not Q are grouped, and then to the right, R and S are grouped. So those are the groups that we have in that example. Let's see this more specifically. A more specific example is, it says let P and Q and R represent the following. P, you get a promotion. Q, you complete the training. R, you will receive a bonus. So in this problem, P, Q, and R have that meaning. The first instruction is A, write that statement, which is given in symbols, as an English sentence. Well, notice that P and Q are actually inside a parenthesis. So that means we have a group there. So when I write it, I'm going to put a comma there. And I wonder if you could see this because it's a little bit small on my screen. But basically, starting with the P, its meaning is you get a promotion. Now, remember that the arrow to the right is a conditional, so you can start by saying if you get a promotion and, because we have the triangle symbol, you complete the training, then comma, which symbolizes that, you know, the parenthesis ended, the grouping ended, then you will receive a bonus. So all together would be, if you get a promotion and complete the training, comma, then you will receive a bonus. So this is how I would translate that. So the comma is important. I know that in math, I always tell the students like, hey, don't worry about your writing. But in this case, we need those commas in there so that we know that you understand which one are the sentences, the statements that are grouped together. Example B says, now it's the opposite. They're going to give me the English and I need to put it in symbols. If you do not complete the training, comma, then you will not get a promotion and you will not receive a bonus. Well, clearly the comma, if you just start by looking at the comma, you will realize that to the right of it, there's a lot. So that needs a parenthesis because that's a group. and all of that is to the right of the comma. So again, go and look at your symbols. It starts by saying, if you do not complete the training, the if is already included in the arrow, so you don't need a symbol for the if. So start with the you do not complete the training, so that's the opposite of Q. And then arrow, and then you start parentheses. Let me write down. So it would look like this. So negation of Q, arrow, and then the comma is indicating that everything else is going to be in parentheses, so open parentheses. And then it says, then you will not get a promotion. Since P represents you get a promotion, so that's the negation of P, so you got to add the wiggle symbol. And then we have an and next, an and preposition, so that means triangle. You will not receive a bonus. Well, the last sentence is similar to R, but R is you will receive a bonus. So if it says you will not, then that's negation R. So all in symbols would be negation Q, arrow, parentheses, negation P, and negation R, close parentheses. So that that compound statement, that long statement, you can represent it is in symbolic form as shown at the end. Okay. Now, these are all of the truth tables. Let me look at the time. I'm doing good time, I think. Let me go very quickly through all of them, starting with the conjunction. The conjunction, it's the and. And when you have two sentences, two statements that are connected by an and, by the triangle, it is only truth when both of them are truth. So these are all of the different values of the possibilities for P and Q. So if you look at all of the tables, you will notice that the first two rows, they're always the same. So I always recommend my students, like just learn the pattern for the first two arrows. I call those the input values. So these are kind of like free values, meaning these are all of the possibilities for P and Q that you can enter regardless of anything, regardless of the whole symbols. So we always start the table usually in this way. So notice that both of them can be true. P can be true and Q could be false. On the very first table, the conjunction. And then on the third line, you could have false and true, and last false and false. If you think about it, since each letter represents a statement, it has two possibilities. It could be true or false. So if you have two statements, that would be 2 times 2, which makes 4. So that's why you see 4 arrows when you only have 2 statements or 2 letters. So if you have 2 letters, you're always going to start the same way. Your table is going to have 4 rows. And it is a good idea to write them always in the same order. It just helps you when you're doing the truth table. And notice, kind of like the final value of the compound statement is on the last column, on the third column. So when you have a conjunction, it is only true when both of them are true. So the next one is called the disjunction. With the disjunction is the or preposition. This is the opposite. So it's gonna be true as long as one of them is true. So if both of them are true, it's fine. If one of them is true, then the whole statement is true. And only when both of them are false, it becomes false. The conditional is a very special one. And this is only false when you start with, when P is true and Q is false. So when you start with something true and you end up concluding something false, then that usually it's a false statement, and it's going to be true on all other cases. The biconditional, this is true when both of them are true, and false when both of them are, and true when both of them are false. and it's gonna be false in the other two cases. And the negation is basically give you the opposite. So if you notice, I have a table that has the values of P, and then it has negation P at the end. So whatever you have for P, then just do the opposite. So if you have a true, the negation will be false. If P is true, the negation would be false. And then if P is false, the negation will be true. And last, you see like on the right bottom corner, there's a table where you would have now three statements. If you have three statements, then now it's A possibilities, just like I mentioned it before, because each one has two outcomes. So you multiply 2 times 2 times 2, that gives you 8 in total. 2 times 2 is 4, and 4 times 2 is 8. So this would be all of the different input values for P, Q, and R. Let's look at an example of a table. So example 2 says construct a truth table. And we always like to remind the students that this will depend on your instructor. So this is a question where you get all of the tables provided. I usually, during exams, exams or quizzes, my students are allowed to have all of these tables. Like either I will print it out for them, or I ask them to write them down before class and they can use them. But it would be a good idea to ask your instructor, like, hey, will I be able to have access to all tables, or do I need to memorize them? Because maybe some instructors may ask you to memorize them. There's also techniques to help you memorize them. As you notice, I was kind of like indicating the patterns before. So right now it says construct a table for NAT P and Q. And let me jump into the table. So as mentioned, there's two variables, P and Q. So start by writing two columns, one for P, one for Q. And the values, you could always write down the same ones. We know that we're going to have 4 arrows because since it's two variables, there's 4 possibilities of truth values. So usually I write them in this exact order. Like the first row will be true, 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 false, false, true, and false, false. Next, you start filling out the table by putting the symbols. So negation P, let me write down. So to fill in the negation of P, I look at the values for P, and then I use, if P has a true, then I put a false. And then I go back and look, and there's another true, then the negation is going to be false. And every time if I have a false, then I put a true. So I start by filling out those values. Next, I do Q. Since there's no negation, I would just copy exactly the same values for Q, which is true, true. So whatever Q has, I input the same values. It's like I'm substituting the letters that Q already has in exactly the same order. Notice that Q has from top to bottom, it's like true, false, true, false. Well, I input exactly the same values. And then at the very end, I put the values of the and right in the middle. And so if you go back and look at the conjunction is false in all cases except when both of them are true. So when you're determining the truth values, you look at the two letters. I have false, true. So that's going to be false. And then false, false, that's going to be false. On the third row, you have true and true. This is exactly when it is true. And true and false, which is false. So I always like to remind my students that that last column is actually kind of like the final value of the whole statement. So that's kind of like the one that matters. Like everything else is partial computations. It's like all of the steps that you need to determine those final values. Those are the ones that we are checking that you can that you can accurately compute. And it's basically telling you that if I were to read it, I would say when P and Q are truth, then the whole compound statement is false. if P is true and Q is false, then the whole compound statement is false, and so on. It's like it determines the values of the compound statement. Okay, let me move on to the next example. So same thing. Notice that I have exactly two letters, even though the Q is repeated. I have parentheses. There's a negation outside the parentheses. Always identify the letters. That tells you how many rows. Now, start filling in the values, and kind of like PEMDAS, you're going to start inside the parentheses. So notice that inside the parentheses, I have negation P, so I do the opposite values of P. Next, I have Q, so I'm going to copy exactly the same values of Q. Now, once you have those ones, there's a symbol in between them, which is the OR symbol, the disjunction. So the disjunction is true as long as one of them is true. So to find out what is the value of that parenthesis, I'm going to put it in between those letters. And so if one of them is true, then the red letter is going to be true. So I have false, true, so it is true. False, false, this is false. True, true, it is true. And true, false, it is true. Now from there, I work to the left. So the truth value of the parentheses appears in red. So now if I work my way back, it's like multiplying by a negative. So it works very similar like numbers. So if the parentheses is true, then the negation would be false. If it's false, then the negation would be true. So the green letters represents the values of that second, the negation symbol, the wiggle symbol that is outside the parentheses to the left. Once you have that, then go on to Q, go and copy the values of Q. Since there's nothing, no symbols next to Q other than the OR, which I'm gonna do later, then I go and copy exactly the same values that Q has. And then to compute that OR, then I'm gonna use green and my rightmost column. So that last set of letters that I did for Q. So remember, since it is an OR symbol, it's gonna be true when at least one of them is true. So in that last space, since I have false, true, then it is true, true, false, it is true, false, true, it is true. And only when both of them are false, then you get a false. So my final values for all these compound statements are true, 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 false. A good idea when you're doing this table is to number. We do that very often. So as you create one column, you number them. Notice that I have 1, 2, 3, 4, 5, 6 columns of letters. So the last one would be 6. That's where I ended. And the first one, which was inside the parentheses, the second column, that would be my first one. So numbering your columns at the end of the table will help you check your answer and check your process. Because you might remember when you're doing it, but then if you look back maybe the next day, it just makes it much easier if you have those numbers so that you know which order you took. Okay, so this is another table. Let me see. I'm gonna probably skip this one. Well, very quickly, this is an example where indeed I actually have the numbers. So notice there's a bracket and there's parentheses. So in this section, like in many other parts of math, the brackets is like another type of parentheses. So they have the same purpose, only grouping, just help us group symbols and statements. So notice when you have like multiple brackets, often you start exactly with let me see what happened. I think I was cut out. Let me go back to that slide. So often you start exactly with the inside, the most inside parentheses. See if I can get back to that slide where I was. So I started by doing P and then negation Q. Then in green, you have the AND connector. Now I work my way outside. So when you have like nested parentheses, like a parenthesis inside another, start on the innermost. That's exactly how you do PEMDAS. You start on the innermost parentheses, and then you work your way out. Then you do the negation, which I represented in blue. And then you go and do P, and at the very end, you do the OR connector. This is very important because often I see students struggle like knowing like where should I start when I do those truth tables. Well, we work from the inside to the outside. Okay, so I'm almost over. Let me see. So I have another example. I'm just gonna go ahead and go through it kind of like fast because I'm running out of time. But I think this is my last example. So if you follow the order of the columns here, I have again brackets, square brackets, and then parentheses. So this is what I call like nested parentheses. So I would start on the parentheses. You could start on either Q or not P. In this case, I started on Q, so I have all of the values of Q, which is exactly the same values that Q has. Those are your input values, so you go and substitute them there. And then number two, you go to the negation of P. That's the opposite of what P has. So if P has a true, then you put a false. If P has a false, then you put a true. Then the next thing, those two are connected by an OR, by the V letter. So remember the OR is true if one of them is true. So it's only going to be false in the second row because you have false, false. And then once you have that green, you go on. Before you can do the AND, you have to put, because connectors, you're connecting two things. So you need to have the two values. We call this like binary operations. You need to have two values in order to determine the final value. So you go next to P, that's number 4. Again, just copy the values. Since P doesn't have any symbols, just copy exact values that P had to begin with. And then using 4 and 3, using those two, you're gonna decide 5, which is the AND. And I can remind you again, the AND connector is true only when both of them are true. So if you have on the first row, you have 4 is true and green is true, so blue will be true. On the next row, you have true and false. Well, that's false because both of them need to be true. If you have false and true on the third one, then the blue is going to be false. And you have false true, then the blue is going to be false again. Then once you have number 5, we haven't finished, then you move out to the arrow. Now to determine the arrow again, so everything to the left is represented with 5. So now you need to have a value for everything that is to the right of that arrow before you can compute the value of the arrow. Since it's negation P, write down the exact opposite values of P. So P has true, false, false, false. I'm sorry, P has true, true, false, false. Then just change that pattern. False, false, true, true. That's your number 6. And now you do the arrow, which is between 5 and 6. And what you're supposed to be doing is that if you compare the table, let me see if I can, if you go and look at the conditional is only false when you have a true on the left and a false on the right. So if I go from blue to 6, from 5 to 6, I have true, false. Well, that's going to be false. So I put a false right there. And then I have false, false. That's going to be true. False, true. That's going to be true. false, true, that's going to be true. And so these are my values on column number 7. Those are my final values of the entire truth table. As I mentioned, when you're doing the conditional, you're looking at the order, like from left to right. It's going to be true always, except when you have true on the left and false on the right. And so in columns 5 and 6, you have true on blue and false on 6. So that's the only case where I put an F. In all of the other letter combinations, I put trues because all of them are true, except when you have true on the left and false on the right. Okay, well, this is the end of my presentation. Thank you so much for listening. And I'm going to pass the host to.
Thank you, Mr. Tintos. We always appreciate your wonderful presentations and taking the time to share your knowledge with us. In the meantime, if anyone has any questions, feel free to post them into the chat. But while we wait on that, let me invite you to next week's sessions. So today in this very room, we are going to have a presentation from EPCC Distance Learning. February 20th, we'll be back again with Happy Math Hour for Math 1332, Conditional and Related Statements, Symbolic Arguments, and Euler Diagrams. For Math 2412, it'll be verifying trigonometric identities and implementing trigonometric formulas. And then for the student success topics, we'll have the EPCC Mental Health Committee with us. It'll be Mr. Christian Salas presenting on learning to love yourself. Thank you all for coming in today, and we would like to wish you a wonderful weekend.